Latency is a critical aspect for REINDEER use cases. For example, if we want to send an order for an actuator to respond to some external event, we would like the network to support this transmission with sufficiently low latency so that the action can be performed on time. Radio waves is a network architecture that offers a trade-off between latency and performance. This trade-off will be the focus of this experiment. We will consider the Lulis testbed, which is a prototype of the radio waves architecture designed to support a total of roughly 1000 antennas distributed into panels. Unfortunately, the full prototype is still under construction, but the current modules can still be used to obtain the latency information associated to the main sources of latency. So let us consider several of these modules connected to each other in a daisy chain topology. The motivation for considering a daisy chain topology is that it allows for full MIMO processing by simply aggregating and forwarding the corresponding baseband data, while no switching is required, meaning that we can significantly reduce the latency associated to sharing data between the modules. A complete schematic of the Lulis testbed would look something like this, where we have several panels of antennas, each one connected through radio frequency chains to the modules previously shown. To achieve full MIMO processing, we should estimate and share some information during the data phase as well as during the pilot phase. Each module will be in charge of computing this information in their local processors. Then, the data would be shared to other modules and aggregated along the way, following a simple aggregate and forward scheme suitable for the daisy chain topology. The final module would then have access to the aggregated data, which could be used to implement a beamforming scheme as maximum ratio combining or an interference cancellation scheme as zero forcing. We should note that implementing zero forcing requires performing a matrix inverse to the aggregated data at a central processor, whereas for maximum ratio combining, the aggregated data can be directly used to extract the user information without any centralized MIMO processing. The system latency is greatly influenced by the frame structure. Here, we see a typical frame structure where some time slots are reserved for uplink pilots and some other time slots are used for uplink and downlink data, with some switching time in between. If we consider the worst case latency, it would happen when the user receives new data just after the last uplink data slot has started. It would then have to wait until the next uplink data slot to be able to transmit its data. The local processing performed at the panel modules would then add some latency, and the modules would then have to share and aggregate the computed data as previously explained, incurring additional latency. If central processing is required, this would also add more latency. Of course, the processing latency should not exceed the available time before the next transmission starts, in order not to flood the network. This time could be extended by considering frame structures with more data slots between the pilots, which would also increase the system efficiency. However, in latency-sensitive applications, the extra waiting time would limit the operability of the system, making it an unsuitable choice here. Here we can see the latency results for the Lulis testbed, assuming a system with 128 square panels, each containing 16 antennas. For a small user density, the latency for zero forcing and maximum ratio combining is similarly distributed, with a substantial amount of latency associated to waiting for the next transmission, a small part of the time dedicated to the local processing at the modules, and a considerable time spent in sharing and aggregating the data throughout the daisy chain front haul. As the user density increases, the zero forcing latency gets dominated by the central processing required to perform the matrix inversion, while the maximum ratio combining doesn't suffer substantial changes. If we compare the latency versus spectral efficiency for the high user density scenario, we can see that as the number of 16 antenna panels grows from 8 to 128, the latency increase is less significant than the achieved performance gain. Also, the zero forcing scheme attains significantly higher latency for a marginal performance increase over the maximum ratio combining scheme, which hints that it's better to add more panels with maximum ratio combining until the desired performance is reached. On the other hand, if we distribute a fixed number of antennas into an increasing number of panels, we can also see that the performance among the different users becomes more uniform, ensuring user fairness and overall system reliability. This endorses the potential of distributed radio waves implementations.